Okay, I'd like to talk about the design and construction of the robot. First of all, this is the controller. It just allows me to change the mode of the robot and to see some telemetry. For example, it lets me see battery voltages, that sort of thing. I can take the back cover off. And you can see we have a microcontroller here. And that's where the code runs, which is written in C. This is an AVR microcontroller chip. This is about a 12-volt stack, which goes into a voltage divider so that I can feed a pin of that into the analog pin of the microcontroller and actually read the voltage in my code so I can display it on the LCD. This is the LCD. This is a serial controller. This is a little perf board here where I soldered on the buttons and soldered the wiring together. So basically this acts as a wiring harness and a place for resistors and capacitors and things like that. And this is a little speaker so that I can get a little bit of a chirp every time you hit a button. And that's about it for that. And then the robot itself, you have the perf board back here, which acts as the wiring harness to solder everything together. And this is the microcontroller here, which is mounted on the board. So all the pins are up underneath the board. Unfortunately, we can't easily see all the hard work under there. And that's a voltage regulator. This is the wireless two-way controller to the remote for starting and stopping and changing mode. This is wireless Bluetooth, which allows me to upload code. I can't upload code over this. It doesn't use the right protocols to program the microcontroller, so I have to actually use Bluetooth to do that. But that also gives me a way to send data to and from the computer while I'm sending data to and from the remote. And then this is a PixieCam, which is a camera put out by Carnegie Mellon. It allows me to do color tracking. And that keeps me from having to mount a lot of sensors on the robot because I can use this to track the beacon, track obstacles. So instead of having a lot of obstacle detectors and a special beacon detector, I can just get away with just the camera. These are industrial motors. They have a gearbox, a motor, and this is an encoder which gives a double square wave, which allows you to accurately determine the position and speed and rotation of the motors. These are lithium-ion batteries, so it's about a 12-volt stack. And then I have 16 line sensors here. Each one of them has a individual wire that has to wire all the way back to pins on the microcontroller. And then I have reflectance sensors here to sense the edge of the table to keep it from going off the table. Oh, and this is motor controller, which I have two-way serial communication to control the motor. Motor also acts as the input for the batteries and regulates the batteries. Okay, that's about it. Okay, I removed the screws that were holding this on, and I removed the nuts that were holding this on so that we can take a peek underneath the perf board, see how much work it takes to wire a robot together. You can see this is mostly the wiring from the 16 line sensors, and then this wiring here is mostly wiring power to different components, and running this here is the two-way serial to the remote. So you can see the remote has a two-way serial radio there, and you can see that radio is also here on this robot, and then has to be wired down to the microcontroller. So these are the microcontroller pins here. Okay, and you can see, let's see, we can disconnect that, and that allows us to see the the row of pins here for the line sensors, and then this is the wiring harness for the motors with the encoders, and then we have a wiring harness that goes out from that to the motors, motor controller. Anyway, I just wanted to show that off so that could be seen. Okay, I want to do a little bit of a demonstration here of the machine vision with the camera. I've got a USB cable here that allows me to send the video to the PC. I can send data over wirelessly, but I can't send the video itself wirelessly, so I need the cable to send it. And so what we're seeing here is, in real time, the camera, and you can see it puts a bounding box around this color. So the camera's doing color tracking on that color. So that's what it sees. So that bounding box, it turns that into data, and I'm able to process that data in a feedback loop. So, and I can demonstrate that if I just disconnect this cable, get this out of the way, and we can turn the remote on, and then turn the robot on. And now they're connected wirelessly over this with this XB controller. There's one in here too, and you can see when I hit a button that the lights flash a little bit there. That's a serial connection, and so what this gives me is a menu of options for the robot. So I can that tells me the robot's battery, and that's the remote's battery, and then this is I can put it into line follower mode, and Cube Quest mode, and Dead Reckoning mode. And then this is the tracking demo. So this will put it into tracking mode. So now you can see it says started. So it will now track this color using the data from the camera. So and then if I want to stop it, I just hit that button right there, and that stops it. You can see it says stopped. So this gives me the start-stop capability in changing modes. That's it for that demo. Okay. And this is actual Robot Rally footage. Setting up the robot here. The pipes here on the table are randomly placed by the judge, so I can't program where the robot's going to find the pipes here. And the object, of course, is to push these pipes off the table. This is called bulldozer. So you want to bulldoze off these pipes as quickly as possible. So the robot with fastest time wins. Obviously, you also want to keep your robot on the table. I missed one pipe there, but the vision system saw the pipe and came back for it. It's in a corner here, so it's kind of tricky not to get a wheel off. So not that unusual for a robot to get a wheel off when it gets in the corner like that. It's trickier than you would think to stay on the table once you're in a corner. That was still a very good run, though, one of the best runs. Okay, now this is a beacon killer with obstacles. So the object is for the robot. The robot is placed in a random orientation by the judge, and the obstacles are in a random placement by the judge. And the beacon is 10 feet away. And the object is to get to your beacon without touching obstacles, or without moving, I should say, obstacles, in the fastest time. So you could graze an obstacle, but if you move it, that's points off. It's significant points off too, so you really don't want to touch an obstacle. Okay, so my robot turned around, and now it has to use its camera to do two things at one time. It has to track the obstacles, and it has to track the beacon. So I have to avoid the obstacles while driving towards the beacon simultaneously. all using color blobs. So you can see it's avoiding the obstacles, and it hits the beacon, and then I hit the stop button. So that the remote allows me to stop the robot here. Most of the other competitors have to actually dive for the robot and grab it because they don't have a way of stopping it. That's the first run. That was a very good time. Okay, and you're allowed a second run. Now in the second run, the judge decided to remove this this pylon. So instead of going around the outside, I'm able to decide which direction I want the robot to start turning. So I decided since he removed this obstacle, I would have the robot turn the other way. So that makes the robot this time, instead of going around the outside, it's going to try and go this way. And that ends up still being a very good path. So here it goes. There. So I'm hitting the start button, and it's using the machine vision. Then I hit the stop button. And I got asked a question here. Yeah, the judge was a little confused. This is Dead Reckoning. The object is for the robot is to hit these 3 circles as quickly as possible and come back across the finish line. And you can't do that using any sort of proximity sensing. You can only do that using your wheel encoders. In other words, you have to monitor the turning of your wheels in order to do this. And the problem with that is there's slippage between the wheels and the floor. So if you go too fast, your wheels will slip too much, and you won't be able to come back across the finish line accurately enough. You'll end up hitting one of these 2 pylons, or you'll go outside of the pylons and you'll be disqualified. So getting a good time here is actually rather tricky, but it's one of these things that doesn't look as hard as it is. But to actually do this, hit all 3 circles and come back and stay between the pylons, it's actually very, very tricky. And I got a pretty good time there. It was one of the better times. Okay, this is Advanced Line Follower. So this is just, I'm using the line sensors to detect the line. This is just a calibration. And of course, you want to get the best time around the track. And it's tricky going through the 4-way intersection here. And it's a pretty tricky course. And that's the first lap, and here's the second lap. This uses a feedback loop called a PID loop, which is proportional, integral, and differential. That's a type of feedback loop you use for this. And that was the end of the performance.